Hello, my name is Daniel Mesenger, and the project that I worked on this semester was to take a fuzzy logic approach to multi-core processor binning. So first, to give a little bit of background on what some of these terms mean. Binning is the act of separating semiconductors into groups based on their performance. So on the right here is an image of a silicon wafer. So this wafer is manufactured and it actually has multiple copies of a die on it. So that's why you see this repeating pattern across this die. So what will happen is this die will be cut into, or this wafer will be cut into various dies, which will be packaged and then sold individually. The trick is that just due to the manufacturing process, each of these products on a wafer will not actually perform equally. There will be slight variations that will actually cause a difference in performance. So why do companies need to bin their semiconductor devices? The simplest answer to that is to maximize the profit. And so the simple way to describe the profit is the price of the sale less the cost of manufacturing the device. But by binning, the manufacturers are able to sell better performing products at a higher price point in an attempt to increase the profit. And these bins are often chosen in an intelligent way to try to increase the profit even more and essentially maximizing it. So a more complicated way to describe the profit here is the sum of all of the price of each bin times the number of each products that are in that bin to get the overall gross, and subtracting the cost from that is to get the profit. So an example here comes from one of my references, and this shows a certain circuit in a certain device that has a latency that can be measured, and this certain latency is critical to the overall performance of the device. And so you can see on the red distribution curve here that most often the delay of the circuit is around 2.4, but it can be greater, impacting the performance of the device. And so these bins are chosen, bin 1, bin 2, bin 3, in an attempt to increase the overall profit of the device. And so you can see the price profile is the blue curve here, and the better performing devices can actually be sold at a higher price point. And so with bin 3, this shows devices that are greater than around 2.7 latency, and these would be sold for the lowest price. In the next bin 2, is a little bit better performing, could perhaps be sold for a slightly better price. In bin 1 would be the best performing with a circuit delay of a less than around 2.4, and could be sold for the highest price. And note that bin 1, the highest price, was chosen to be a more likely bin for the devices, so there'll be more devices in this bin, meaning more devices that can be sold at the highest price point. And so these bins were chosen in this way to attempt to increase and maximize the profit for this product. But binning comes with a cost. So as mentioned again, profit is the gross sales minus the cost, but the act of binning itself is actually incurring a cost in the manufacturing process. So binning requires extra steps in manufacturing. It requires designing extra pieces into the process. For every single chip needs to go through this process to be binned. And also, the more accurate the binning is required, the greater cost there is too. So you could come up with a very extravagant scheme to separate devices into many different bins in an attempt to have different price points to sell at, but the act of doing so could be such a great cost that it actually negates the value in having the many different bins. So it's very important that the cost of a binning process doesn't outweigh that increase in profit. And so it's often a trade-off when designing the binning process so that the maximum profit can still be obtained. So binning for multi-core processors can be particularly difficult. So the same basic concepts apply to multi-core processors as the other devices previously mentioned. So each core in a multi-core processor will have slight variations due to the manufacturing process and will actually perform differently. So the performance of a single core in a multi-core processor is usually measured by the maximum frequency at which the core can operate before it begins to fail. And so in a manufacturing process, if you want to find this frequency, this is typically measured with a pass-fail type of frequency test on the core. So these tests will be applied to this core, and the frequency can be increased until it's found that the core is no longer passing this certain test, in which case that that is no longer operating at that frequency. And so that's how the maximum operating frequency can be found. And so as stated before, this type of test in manufacturing adds cost, therefore decreasing profit. So as it can be expensive to find the true exact maximum operating frequency of a given core in a manufacturing process, there's a trade-off to be had here when running these frequency tests. What is typically done is that a fixed set of frequencies are tested, and these frequencies are not tested linearly from slowest to fastest, but it's actually tested in a binary search fashion. So the set of frequencies is split down the middle. Whether that pass fails or not, the remaining half of either faster frequencies or slower frequencies are then split in half, and that frequency is tested. And so the worst case of finding the operating frequency for a given set of frequency values in the test is the ceiling of half of the frequencies being considered and tested. So those are some of the details on how a maximum operating frequency for a single core can be actually measured in manufacturing, but it becomes a little bit more complicated now when talking about a multi-core processor, so a processor made out of many of these single cores. And so it can be a challenge to actually infer the overall performance of a processor with many cores just by looking and testing single cores. And the performance of a multi-core processor is actually going to be different under different applications. So two main types of applications that I'll discuss in this project are multi-thread applications and multi-program applications. So a multi-thread load or a multi-thread application would be a single program that has multiple threads that are running together across multiple cores on a processor. And these threads would be interacting with one another to accomplish to process some information. Where a multi-program application would be a load where each core on a multi-core processor is executing its own program that's not interacting with other cores, and so the overall performance is different based on the single cores in a multi-core processor. Next, I'd like to discuss a couple bidding processes, non-fuzzy bidding processes that are currently used and currently under research in the field. So the first of which is the minimum of maximum bidding process, or you'll see for the rest of this presentation shortened to min-max. And the min-max process essentially scores the overall throughput of a multi-core processor based solely on the slowest core of the processor. So the minimum operating frequency of the maximum operating frequencies for a multi-core processor. So this type of binning method best correlates to multi-thread applications. So these are applications in which all of the cores are being used in a single program with multiple threads and are interacting, so the cores are interacting with one another. And so this makes sense as oftentimes the slowest core will be bottlenecking the overall performance in this type of application. And it does not correlate as well to multi-program loads, where just because one core is slowly working on one program another core is individually working on a totally separate program and not interacting with one another, in which case, with the min-max binning method, the effect of the faster core is totally thrown out and not taken into consideration. So here is another graph from a reference that mentions these two types of binning methods. And so the black line here represents the min-max correlation to throughput, right? 1 being a true correlation to throughput across number of bins here. And you can see as you increase the number of bins, the black line in a multi-programmed load, where the min-max does not do as great of a job as categorizing, does not quite approach the true throughput. For a multi-threaded application, what the green line here is showing, it does, as you increase the number of bins, approach a true correlation to throughput. And this is due to the reason that I mentioned before, is that these types of applications truly are bottlenecked by the slowest operating frequency of a single core. And so that's why this method does a good job of correlating the throughput in those situations. The second non-fuzzy binning method that I want to discuss is the sum binning method. And so this method scores the overall performance of a processor, the overall throughput, based on the sum of all of the maximum operating frequencies of each core. So in this case, each single core's operating frequency has an equal effect on the measurement of the overall throughput of the device. Meaning that one slow core, unlike in the min-max method, won't completely bring the overall performance of the multi-core processor down. It will affect it equally as a faster single core would affect the performance. So logically, this correlates better in the opposite fashion as the min-max method. So this better correlates to the multi-program application, where there are multiple individual programs running on each core and not interacting with one another. Therefore, the slow core does not have an effect on a faster core doing its own separate processing. But it does not correlate well to multi-thread applications, where the slower core really does dominate the performance. But in this sum binning method, it has an equal weight in the measurement. And so this is actually the same graph that I showed earlier. Just want to focus on the other line. So the sigma F, the blue line, and the red line are the sum binning method. And you can see that it does in a similar fashion for multi-threaded programs, where it does not correlate as well, does not quite approach true correlation to throughput, where for multi-program this does. So it essentially behaves oppositely as the min-max method does. So for this project, I wanted to propose a fuzzy method of binning these microprocessors that does not rely on a truly mathematical operation such as a min-max or sum to better evaluate the overall performance or the throughput of a multi-core processor based on the individual cores, where we can think of this logically or in linguistic terms to describe how the single core's operating frequencies would affect the overall performance of the device. So first, some highlights and an introduction to the fuzzy binning process that I had designed. It is also based on the maximum operating frequencies of each individual core in a multi-core processor. So this is the same as the min-max and the sum binning methods that I had just discussed previously. However, unlike these methods, it combines these operating frequencies in a fuzzy manner in an attempt to estimate the throughput of the device rather than combining them in a solely mathematical fashion. So this fuzzy binning process that I've designed uses a hierarchical structure in an attempt to reduce the number of rules. There can be many cores in a multi-core processor. 4, 8, 16, even up to 64 or greater, and this number is expected to just increase over time. So it was important for this design that as the number of inputs, right, each core of a processor is an input to this fuzzy binning process, that as we increase the number of inputs, that this design can actually scale, and that's why it's important that this be based in a hierarchical structure to try to reduce the number of fuzzy rules. So the first step in my fuzzy binning process is to fuzzify the inputs, and in this case, all of the inputs for this process are the operating frequency of each single core of a multi-core processor. So how I've done this is to create a linguistic variable for the frequency of a single core of a processor. And in this design, any number of frequencies can be used. In my example that I'll show later, I used 5 nominal frequencies. But the fashion in which these are combined are through triangular membership functions. And so you can see on the right, this shows how these are combined. So for a given frequency, we can call it F1. For that frequency's bin, it is a 1 at that frequency with a triangular fashion to the adjacent frequencies that are being used. And so it is not required for this design that these frequencies be evenly spaced. They could be arbitrarily spaced on a scale. And so this would be important for fine-tuning how these frequencies are described throughout the binning process. So when it's time to try to optimize and maximize the profits using this binning process, these are some of the knobs that can be turned in an attempt to do so. The second key linguistic variable that was important for this design was to describe throughput. And so all throughout this design, you'll hear throughput being used as a fuzzy term. And so this is how I've defined it for this system. It is a universal discourse in the range of 0 and 1 inclusive, where 0 is the worst possible throughput for a device, but still saleable. So this is not a failing device. This is just the absolute minimum that a device could perform and still be considered for sale. And where 1 would be the best possible throughput. And so similar to the frequency bins, these throughputs bins are also combined in or defined in a with triangular membership functions. And just like the frequency bins, these bin values, which would be numbers between 0 and 1, do not need to be evenly spaced, and there does not need to be the same number of these throughput bins as there are for the frequency bins. And so again, this would be something that can be tuned and optimized when attempting to maximize the profit, would be actually selecting the throughput values between 0 and 1 that these triangular membership bins would be based on. And so this is an example of what this fuzzy binning process would look like for a 16-core processor. There would be 4 levels in this case, and there's 2 types of sub-fuzzy systems that would be 2 input and 1 output systems that make up this hierarchy. The first would be for level 1. And level 1 in this system takes 2 inputs in the form of the fuzzy frequency, so the fuzzified frequency input, and outputs a throughput score. So this is an attempt to look at 2 cores of a processor and combine them into how they would affect the throughput of the overall system. And so these are fed together like this. So all the systems in level 1 are identical, with 2 cores being fed to 1 with 1 output coming out. And the rest of the levels, level 2 plus, take 2 throughput scores and combine them together using fuzzy rules into 1 throughput score. And so this is done until we're left with just 1 throughput score that is a summary of the overall performance of the device. And so this would be a linguistic variable of throughput, as I mentioned before, well, that will then be defuzzified to a value between 0 and 1. So each of these fuzzy systems that make up the overall hierarchy are based on a rule set. And so this rule set is an attempt to look at the two operating frequencies of the input cores and describe them in a fuzzy term that represents the performance of the device. And so here's an example of a rule set for the level 1 hierarchy, or the level 1 in the hierarchy, where you have frequencies on both sides of the matrix. And so these would be the frequency bins that are selected. So the triangular membership values, membership functions for the input frequencies. So you'll notice that logically this relationship is symmetrical, right? So there is each core on the two cores that are being considered has equal weight. And so, if one core is F2 and the other core is F0, that you get B1, but that is identical for the other direction. So if one core is F2 and the other core is F1, you'll also get B1, and that's because the cores have the same weight on the effect. And so by logically, all of these rule sets are symmetrical. So the difference for the level 2 plus rule sets is that they're no longer looking at frequencies for the inputs, they're also looking at throughput scores. And so this is an example rule set to combine throughput of two cores into an overall throughput. And so just to take a look at some of these entries, we would know that if there's two very good performing cores before, then you get an overall performing processor, also B4. But perhaps if one is just slightly worse, a B3, but still very fast, and the other one is the best B4, the overall throughput in this application, example application being described here, would still maybe be the best B4. So now that I've discussed the overall design of this fuzzy binning system, I want to get into some of the actual implementation details of how I was able to implement this system and evaluate its performance. So this design was implemented using MATLAB and Simulink, and then simulated so that I could see how the fuzzy binning system performs against the min-max binning system as well as the sum binning system. So actually all three of these systems were implemented in MATLAB and simulated on two sample data sets that I had created to compare how they perform versus one another. So the performance of all three of these binning methods I've measured, collected some data and evaluated it, and we'll discuss later in this presentation. So as I mentioned, there are two different data sets that I have used in this process of simulation. And both of these data sets represent a batch of 1,000 processors that have 16 cores each. So in other words, a batch of, a manufacturing batch of 1,016 multi-core processors. And the operating frequency of each of these single cores on this multi-core processor is in the range of 4 gigahertz to 4.2 gigahertz. So anything outside of this range is not considered. So anything less than 4 gigahertz would be a failing device and not part of the binning process. And in this case, 4.2 is just a theoretical maximum that is needed to configure the range for this simulation. And so the difference between the two data sets is that the first one has a evenly distributed random operating frequency for each core. And so in this case, we're using basing the operating frequency of this data set for each single core based on a random variation in the manufacturing process, which is sometimes considered. In the second data set, this is a normally distributed random value in the range of 4 to 4.2 gigahertz, and this is normally distributed around 4.1. And so in this case, this data set looks more like there are more single cores of the processor that are going to operate around 4.1 gigahertz and less around the edges, whereas in the first data set, this is evenly distributed across. And so I created these two data sets to see how each of the binning methods, the fuzzy and non-fuzzy, would perform with the different variation models for the manufacturing of these multi-core processors. So the first step in the implementation for simulation was to actually create each of the 2 input, 1 output fuzzy systems in MATLAB. And to implement this, I used the Mamdani Type 1 implementation. And since the range of these processors was in the range of 4 to 4.2 gigahertz, I selected my 5 fuzzy frequency values to be 4, 4.05, 4.1, 4.15, and 4.2. And so you'll note that in the case for this example, these frequencies are evenly distributed across the range, but it's not actually required for that to be the case when actually going back and tuning this binning process if it was actually being used. Same goes for the 5 fuzzy bins for the throughput scores. These are in the range of 0 and 1 and evenly distributed. I selected 5, which is the same number of frequencies, but again, not required. This could be less than 5, could be more. It does not have to be the same number as frequencies, and it also does not have to be evenly distributed across the range. There could be more bins up closer to the better performing processors in an attempt to maximize the profit, or any other way that these bins could be defined to try to optimize. And finally, each of these systems that are built into the hierarchy use the centroid defuzzification. So after the if-then rules are executed, the centroid defuzzification method is what's used to come up with the throughput score that's in the range of 0 to 1. So these tables represent the rules, the relationships that I had chosen for implementation of correlating the frequency of 2 cores into a throughput score. And this was also implemented in MATLAB using the rule editor, so every possible rule was actually defined. But again, the idea of this fuzzy system binning process would be that this table could be edited as we learn what the actual effect of certain cores are on an application. And so what provides the flexibility here is the ability to actually change these rules and how we combine the single core's operating frequencies and how we correlate them to the throughput, rather than just relying on mathematical operations like sum or min and max. The next important piece to the simulation setup is a MATLAB setup script. And the purpose of this script is a few things. The first is to actually set up the workspace for the Simulink simulation so that a lot of things are parameterized, so that I could run this simulation multiple times, tuning different parameters and learning results from that. And also, this setup script performs the frequency tests that I had mentioned previously in this presentation. So the data set was created and has what represents the exact maximum operating frequency for each core of the processor, but in reality, it's unrealistic to try to identify that exact maximum operating frequency, and it would be way too expensive in terms of cost in the binning process. And so this script simulates that binary search test that I had mentioned earlier, and actually then provides a simulation with frequencies in the discrete values of the frequency range that we are looking at. So an example would be, if we wanted to only do 15 tests, the script would only test that data set at 15 evenly distributed values in the frequency range, and so that each of those single core processors would then be, the maximum operating frequency would then be converted to one of the discrete points in that data set. And so this whole process is very important to the simulation in that it gives us realistic results rather than just assuming that we're able to find the true operating frequency of each individual core, because that's not the case in actual manufacturing. And so, as I mentioned, this script does contain a few configuration parameters that can be used to help set up the simulation. So I'll just go over a couple of these. These are all of the parameters. You can set the range of the frequencies to be considered. So in the case that I'm mentioning here, the minimum would be 4.0 and the maximum is 4.2. We can specify the number of cores for the processor. And so again, in our example that I'll be covering, this is a 16-core processor. The number of samples to generate for the data set. In our case, we are doing 1,000 samples. So for each, there's 1,000 processors that will go through our simulated binning procedure. The number of tests is also very important for the simulation. So this, you'll see that I vary and get different results when varying this. So this would be the number of tests performed to find the maximum operating frequency of each single core processor, each single core of the processor. And so as this number would be increased, right, if we were doing 1,000 tests, say, on each core of the processor, we could probably get a very close estimate of the true exact operating frequency of that core, but that would be very expensive to test each core, 1,000 times. And so you'll see as I cover the results, the effect of changing the number of tests in the binning procedure. There's also the ability to set the bin thresholds. And so at the very end of the process, when we need to actually come up with a crisp bin that the processor would be placed in, these bins are based on throughput scores between 0 and 1. And so there's the ability to actually set what would be the minimum score for a particular bin. So an example of the best bin might be a minimum score of 0.95 out of 1 to be considered the best performing processor in the batch and then to be placed in the best bin. And so that's also something configurable as part of the setup script for the simulation. This is a image of the very top level of the Simulink simulation, just to give an idea of what this looks like and how this is being implemented. So it basically runs the 3 binning processes in parallel on the same set of data. So all of this coming in is the same data set that's being separated out into its 16 cores and fed into each binning procedure. So that's how the input to the system, and the output is a bin for each processor in the data set. And there's actually 3 outputs because there's 3 binning processes being tested. There's an output bin given for each processor based on each binning process that's being used. So the fuzzy binning method is implemented in Simulink using the fuzzy inference system that was set up in MATLAB that I had shown previously. And this is what that hierarchy looks like. It looks very similar to the concept diagram when actually being implemented in Simulink. So all the inference systems in level 1 are of the same type. Actually, so all of the systems in this row or this column are identical, where they take 2 fuzzy frequencies to output a throughput score based on the 2, where the rest of the columns in the hierarchy are all of the second type of inference system, where the 2 throughput scores are inputs and 1 single throughput score is the output, and until we're left with 1 throughput that represents the combination of all 16 single cores of the processor and how they will perform. The sum binning is implemented using just a simple sum block in MATLAB. So this is exactly what was described previously, where the actual binning metric is just the sum of the maximum operating frequencies of all of the single cores in the processor. But you'll notice that in order to compare, we need to normalize the output of this bin to our same 0 to 1 scale so that we can actually compare across the different binning methods. And so the normalization of the sum binning method is essentially just an average, actually. So this is how it's implemented in MATLAB, just using some of the math blocks. But the output of this then is also a throughput score on a scale of 0 to 1. So it's essentially just the sum of all the maximum operating frequencies normalized to that scale, and that's the actual math being performed here. The min-max is very similar to the sum binning method, where the block is actually just a min block from Simulink, just like the sum was just a sum block. And the normalization of this block also needs to be done to put the score of the performance into the same scale of 0 to 1. And this normalization looks also a lot like the normalization for the sum without the need to divide by cores, because there's no need to take the average in the sum. We already have something in the range of the frequency range of 4 to 4.2. So this is how that normalization is done and implemented in Simulink. So the final step in the simulation is the actual, what I've been calling crisp binning, which is the process of actually selecting a bin. In my case, I'm using 5 bins labeled 0 through 4 based on the throughput score that was calculated in the range of 0 to 1. And so this is implemented in MATLAB just using threshold gates. These were the rules for the bins that I have set up. So the worst performing bin is anything with a throughput score of less than 0.25. The next bin up is between 0.25 and 0.5, and so on until bin number 4, where the throughput score is anything greater than 0.95 would be the highest, best performing bin. So anything in the essentially the top 0.05 in the scale of 0 to 1. Finally, I'd like to cover the results of the simulation that I performed and look at the binning performance of all of the binning methods, and also highlight the comparison of the fuzzy method that I have designed compared to the non-fuzzy methods used for binning this sample set of processors. So this table shows all of the simulations that I run and that I had ran and what was varied throughout the simulation. So a total of 24 simulations were run. There were 12 simulations run on the even data set and 12 simulations run on the normally distributed random data set. Each of these sample sets, the number of tests were varied between a small realistic number like 15 up to 3,500 tests, frequency tests, to try to identify the exact operating frequency of each individual core. And so this provides some useful information on looking at the cost of each binning method and how many frequency tests are needed for the binning method to actually be successful. So something important an important term that I'll be using to describe the performance of these bins is missed bins. And so what can happen is, due to the finite number of frequency tests that are run on each core of the processor to identify the maximum operating frequency, it's possible that the frequency that is selected is not true or not close enough to the exact operating frequency of a core. And so because the way this frequency test is designed, though, the frequency that is found to be the maximum will always be less than or equal to the true exact maximum. So it's not possible to place a processor in a bin that is actually greater than it should be, but it is possible to place a processor in a worse bin or a lower performing bin, when in reality that processor would actually be performing, would be capable of performing in a higher bin. And so this is what I'm calling a missed bin, and this missed bin metric is one of the ways that I am measuring the performance of these different binning methods. So this table shows a curve of the missed bins for the fuzzy binning method on the evenly distributed data set. And so you'll see it's very clear that as you increase the number of tests, you miss less and less bins, and that you get a more accurate binning process for each of your processors. And so starting out at only doing 15 frequency tests on a core, the fuzzy binning method actually misplaced 279 out of the 1,000 bins, so that's pretty high. But as we increase the number of tests, this does very sharply decrease into a more reasonable amount. And it wasn't until we got all the way out to 3,500 tests per core, which would be a very, very excessive amount of tests, that we actually found the exact true bin of all the processors. This is a curve that shows the same fuzzy binning method, but on the normally distributed data. It's very similar. It starts out at about the same, decreases sharply. However, it never actually, in the amount of tests that I had run up to 3,500, it never actually does find the true bin of each processor in the data set, but it does quickly decrease as we would expect as we increase the number of bins, and then starts to settle out. Here's another similar curve for the sum binning method. And a little bit later, I'll directly compare these so we can look at the performance, but just a quick highlight on the sum binning method. It misses less bins initially at its 15 tests, and it also quickly decays down to a very reasonable amount of missed bins in terms of cost with the number of tests for that device. And another curve here showing the same sum binning method on the normal distribution, the normally distributed data set. Same thing, starts out at a high amount of missed bins, but as we increase, we very quickly get to something reasonable in our missed bins. And so this missed bins metric is very important to maximizing the profit. So every bin that we miss would be a missed opportunity for selling a processor at a higher price point, which is why it's important that we try to minimize the amount of bins that are missed. So here's a summary of the performance of each of the fuzzy binning methods on the normal data sets and the sum binning methods on the even and normal data sets. So on the top row here, these are both the fuzzy binning method results on the even data set and the normal. And in the bottom row, we have the sum data sets on the even and the normal. And so when we compare the two, they're comparable. The fuzzy binning method is not extremely more costly than the sum binning method, but if we look closely, it is slightly more costly. So at each data point on the x-axis, at each number of tests, you'll see that the sum binning method was performing better at that number of tests. And so if we look at kind of a summary of the table here, in all cases, like I said, the fuzzy binning method had a greater cost than the sum binning. But what's important also is that the cost was still comparable. It wasn't extremely more costly to do the fuzzy type of test, which will be important when we discuss some of the benefits of the fuzzy test. So on this table here, what I have summarized is the percentage. So these would be different benchmarks for the missed bin percentage, right? And so in this case of 1,000 samples, a batch of 1,000 processors, 10% would be if we missed, when we missed 100 bins or less. And so if we look at the performance of the different distributions for the different fuzzy and sum binning methods, in every single case here, the sum binning it took slightly less frequency tests to come to meet this percentage. So in the case of 10%, it took 100 frequency tests per core to meet 10% missed bin percentage, where in the sum binning method, it was only 30. And this pattern can be seen throughout the results here on this table. That the fuzzy binning method was slightly more costly than the summing binning method was, but still comparable. And there were some added benefits of using a fuzzy binning method compared to the summing binning method. And the most important being that the fuzzy binning method does not share the limitation on the correlation to throughput that the sum binning method has. So if you remember, as I discussed earlier, the sum binning method does a good job of correlating the actual performance to the real throughput only in multi-program applications. So these are applications, as I mentioned, that are running individually on each core and not interacting with one another. Now, the fuzzy method does not share that. So we can describe our fuzzy rules for any type of application. And it's also not the case that applications are always either multi-program or multi-threaded. A processor could be used in an application and have a load that is a mix between the two. It can be running multiple programs, some programs that are multi-threaded, some programs that are multi-program. And in this case, we can actually describe the correlation to throughput using our linguistic variables and our linguistic terms to better correlate to throughput based on our single cores of our processor by learning how it actually affects a particular application or a particular load. Of single core frequencies to the overall throughput of the application linguistically and intuitively. So where sum is limited just in adding up all the numbers, we can say things that we know about a given application. Like, for example, if it were the case that processors with at least one fast core will always perform above average, but processors with any slow core always perform the worst. If we know that about a certain application, then we can use this to build our fuzzy rules and better describe how the single cores of a processor will affect the throughput of a device. And we can also extend this out. I mean, this design was only using looking at 2 cores at a time to come up with the performance and building these into a hierarchy to minimize the rules. But we could extend this concept out to looking at something with more than 2 cores at a time. So an example here a couple examples would be as long as a processor has at least 2 OK cores, the performance will be okay, right? This is a fuzzy term, and we can input this into our fuzzy system to try to gauge how a device will perform and bin that accordingly. Another example would be, if 2 cores are greater than or equal to F2, the performance will never be B0, right? So this is a more specific example related directly to the fuzzy, the linguistic terms for the frequency and the bins that have been described, but we could directly input this rule into our system if we know that this is true for our application. There's also some room for improvement with the fuzzy binning method, right? If let's say we don't know how the frequencies of single cores actually affect the throughput in a certain application or a certain program load, it could be possible to train this fuzzy binning method using a neural network, right? So we don't actually know at first how these single cores will affect the overall throughput, but we can actually perform the tests and measure the throughput with a processor, a real manufactured processor running that application, and feed that back into our fuzzy system to kind of dial that in and to where we can actually learn the effect of the single core operating frequencies on that particular application. So to summarize the performance of the fuzzy binning method compared to the non-fuzzy, it was shown that in all cases in my simulation, the fuzzy binning method was did come with an added cost compared to the sum or the min-max bidding methods. But the cost was still comparable. It wasn't extremely off. It wasn't extremely more costly to use the fuzzy method. So as long as we could negate some of that added cost by improving our bidding capabilities, it could actually be justified to use a fuzzy bidding method. And this fuzzy bidding method does have some advantages that could be used to actually increase the profit, right? It has more knobs that we can dial. We can better correlate the bins to throughput in a real application. We can vary the bins on the scale of that throughput score, and we could tune these parameters in an attempt to gain more processors at higher price point, and therefore increasing the profit, which is the whole goal of the bidding process. If you'd like some more information on any of the papers that I had used to gather some of this information, here's some of the references that you can check out.